Hey, hey. Section 2. Differential equation still, but now we're talking about growth and decay. So now we're getting to like applied problems, not slope fields. The section and the next one, so the rest of the chapter, develops strategies and techniques for solving differential equations known as a separation of variables. This is a very, very important thing that you need to know how to do. The goal with this technique is to get everything involving each variable on separate sides of the equation, hence separation of variables. If you do that successfully, then you can integrate both sides using any method that you've learned for integration to arrive at a solution, but you are integrating both sides at the same time. Separation of variables on the AP? Most definitely. It is always there, and it's not just one problem. It's all over the place. So you definitely need to know how to do this. All right, your first example. Solve using a separation of variables. We have y prime equals 2x divided by y. So the first thing we need to do is separate the variables. Y is on one side, x on the other. So what should we do? All right, if you multiply both sides by y, then you wind up with y prime equals 2x.
We can do that. Let's do it. I'll take the derivative.
I don't want to take the derivative. I already have the derivative.
For y. What are we doing?
This is not the way you're supposed to go. Exactly. What I want to do is rewrite this y prime as dy over dx equals 2x over y. And already you know what to do. What do you do? Rewrite this as a differential equation with y on this side and x on this side. So we are going to multiply both sides by y, but we're also going to move this dx over here. So I wind up with y dy over dx equals 2x. And now write this as a differential. Y dy equals 2x dx. That's your separation of variables. Now you still have to integrate. Integrate. We're solving. We want just, we don't want y prime. We want like the original function. So I'm going to integrate both sides. That also takes out the dy and the dx.
So we get 1/2 y squared.
Good. 1/2 y squared
Equal to x squared.
plus c.
We have to put plus c on this side.
Okay. There's a constant over here and a constant over here. If I subtract the constant from over here, I wind up with a constant minus some other constant, which gives me just another constant. So just plus c on the other side is fine. Good question, though. Okay, now, what? Sure, multiply both sides by 2, and I wind up with y squared equals 2x squared plus c. Because 2c times a constant is just a constant.
Now,
No.
no, not square roots.
Now,
Now,
we're just going to move this over here.
I do not understand. What are we solving for?
Nothing. This is it. You could take the square root of both sides to get y, just y, but you have plus or minus over here. We don't have to do that. We're not doing that here. So I can move this y over here and get 2x squared minus y squared. And then I can move the c to the other side. Negative c is the same as c, so I just write c. There's your answer.
Because it says solution in the book.
There's some other answers that could happen here. If I subtracted the 2x squared from both sides, I'd wind up with y squared minus 2x squared equals c.
but we don't know what c is.
We don't know what c is, so it just remains c the whole time. I could call this one here c1. I could call this c2. I could call this c3, but it's still just a constant. It doesn't matter. So the answer is preferred to be in sort of like standard looking form. Alphabetical order, no fractions, things like that. We want to check this answer to make sure that we're right. We should wind up with an answer that kind of looks like that. In order to check this answer, we need to differentiate implicitly. So, off to the side, check. Take the derivative. What do we get? 4x minus 2y dy over dx, which I can rewrite as y prime, equals 0. How about I divide everything by 2? And now I have 2x minus y prime equals 0. Move the negative y prime over and then reverse it. Y prime equals 2x. Divide by y prime equals 2x over y, which is what we started with. So we do have the correct answer here, and this is an appropriate method for solving a differential equation like this.
Suddenly a K.
All right, growth and decay. This is the crux of the whole section right here. The main thing to remember for growth and decay is the rate of change of a variable is proportional to the value of the variable. The rate of change of something is like a dy over dx type situation. But if we're calling it growth and decay, then we're talking about time. So it's not dy over dx, it's dy over dt. So we have dy over dt is proportional to the value of that variable. So dy over dt equals some constant times that variable. Okay? So k is a constant of proportionality. We're going to integrate this to find our general solution. So we need to do a separation of variables again. We have dy over dt equals k times y. Separate the variables. dt winds up over here. Divide by y. We'll leave the k on this side. So we wind up with 1 over y dy equals k dt. Are the variables separated? All right, so now we're going to integrate. What is the integral of 1 over y? Natural log y, yeah. Equals. Do I need absolute value? Just that?
Yeah.
Okay. All right. Equals what? That's a constant.
So K-Y.
It's just kt. We probably should have a plus c. We're fine. Now what? Make a base e on both sides. Why would you do that? To get rid of the natural log. Yeah, we can actually get y by itself here easily, and we're going to if we make a base of e on both sides. Trust me, that's what we're doing. What happens on the left side? It just becomes y. Now on the right side we have e to the kt plus c. That can be simplified. That can be simplified. It is a growth and decay thing, but we want to simplify this exponent. To do that, we need to remember a property of exponents. If I have like bases, a to the m times a to the n, and I multiply them together, what do I do with my exponents? I add them. So I wind up with what we have is this case, we're going this way. So I want to turn this into y equals e to the kt times the same base, e to the c. What is e to the c? No. E to the c, what is that? No. Yes, it's c, it's a constant. It's just a number. So that makes it a c, which means this thing turns into e to the kt times c, or y equals c times e to the kt. And that is your general solution for exponential growth and decay. That's the way you do it. So the general solution is y equals c e to the kt power. And this is the equation you're going to be working with a lot in this section. If k is greater than 0, so if that number right there is greater than 0, we're talking about exponential growth. If k is less than 0, we're dealing with exponential decay. To find the value of c, so this number here, and the constant proportionality k, you just need to apply an initial condition or two other given conditions, or the initial condition and another given condition in order to find those two things. It's basically like you have two variables, two unknowns. You'll have to come up with two different equations. Sometimes you have to be sneaky if you're not given enough information. So we'll do a problem or two that are like that where you have to be kind of sneaky. Yeah, sneaky's good. All right, so here's an example. I'm giving you the equation again, and it says the rate of change of y is proportional to y. Then it tells you a couple of initial, like an initial condition and then some other condition. We can use those two things to figure out what c and k are. And then answer the question, what is the value of y when t equals 3? So, when t equals 0, y equals 2. All I got to do is substitute in those values. Y is 2 equals c e to the k times t is 0. Well, k times 0 is just 0. E to the 0 is 1. So I wind up with c times 1, which is just c. So 2 equals c. So now I have y equals 2 e to the kt. Now the other one, t equals 2, y equals 4. So I have 4 equals 2 e to the k times 2. If I divide both sides by 2, then I have 2 equals e to the 2k. So how am I going to get that 2k out of the exponent? Take the natural log of both sides. That's right. Natural log, natural log. Natural log of 2 I can't simplify, but this just becomes 2k. So I have natural log 2 equals 2k. Divide both sides by 2. The natural log of 2 divided by 2 equals k. And now on your calculator you would type that in to get the decimal version of that, rounded to 3 or 4 decimal places. 4 would probably be better in this case. So your final equation would be y equals 2e to the what? Give me 4, yeah.
3, 4,
So 0 point?
yes, sorry, 0.3464.
T. And that would be the particular solution for this problem. Now find the value of y when t equals 3. It's as simple as plugging it straight into this equation, y equals 2e to the 0.3466 times 3. And my suggestion to you is to use the answer that you got from doing this. Don't round it. Don't use your rounded answer. Or retype natural log 2 divided by 2 and then times 3 to get that exponent. So that is the exact exponent that you're supposed to have. You get y equals what? Six, 5, 6, 8. So 6, 5, 7. And there you go. That's how you do these problems. Fairly easy, yeah.